Hey, what's up, you guys? So, in our previous videos, we covered questions 1 through 8, and in this session, we will proceed with question number 9. So, this one right here. Now, before we begin solving, let's go over our usual steps for approaching the problem. So, our first step is to substitute power series representation, y prime, and y double prime into our main differential equation. Our second step is to match the exponents or the powers of x to n. So we need to make sure that all the x's of the multiple power series that we have, they all have the power of n. And then our third step would be shifting the indices of all the power series we have. Okay, and remember the third step comes after the second step, so we will try to shift them after we transformed them so that their powers or their exponents have been transformed to n. Okay, and then like I said earlier, I will always keep the larger index. So the power series that has the largest index will stay as it is, and we will try to shift the indexes of the power series which has a smaller value. So the smaller value starting index power series, they get shifted. Okay, and then we have our fourth step, which is combining the series to one. So after we have performed our second step, that is making sure that all the powers of the power series has the power n, and also all the indices of the power series start from the same index, then now we can combine them into one. And after performing the fourth step, now we will find the coefficients, okay, and we use our recurrence relationship in order to do that. And then right after determining the coefficients, we can finally find the general solution. In this form, I've constantly applied these steps to every problem I've solved, so all the problems in section 4.1 follow the same approach. So without further ado, let's dive into the problem. So in our today's problem, we have y double prime plus 1 minus x, that's in the parentheses, y prime plus 2y equals 1 minus x squared. Now, in our first step was to substitute each y term into a power series form within the main differential equation. So let's go ahead and do that. So we know that our y is summation n equal to 0 to infinity a sub n times x to the power n. And we already know that goes under our red box. And then we have our y prime, which is summation n equal to 1 to infinity a sub n times x to the power n minus 1. And this goes under our green box. And then we have our y double prime, which is summation n equal to 2 to infinity a sub n times n minus 1 times x to the power n minus 2. And this falls under my blue box. Okay? So now we have our power series form for y prime, and y double prime. So let's go ahead and substitute each y term into my power series form within the main differential equation. So we have our y double prime. So I'm going to write summation n equal to 2 to infinity a sub n times n minus 1 x to the power n minus 2. And then plus 1 minus x parentheses, and then I have y prime, which is summation n equal to 1 to infinity a sub n times x to the power n minus 1. And then I have my plus 2, and then I have my y, so I have summation n equal to 0 to infinity a sub n times x to the power n equals 1 minus x squared. Okay? Now I'm going to distribute these 1 minus x to my second power series. So doing that, I will have summation n equal to 2 to infinity a sub n times n minus 1 x to the power n minus 2. And then plus, so 1 times my power series, my second power series is basically my second power series. So I'm just going to write that again. Go to 1 to infinity a sub n times x to the power n minus 1. And then I have a minus because there's a minus sign in front of x. And now x gets multiplied with my second power series. And I can see that there's already x in my power series and there's an x outside my power series. And when I'm multiplying them, since they have the same base, that means their exponents adds up. And if I add up the exponents for my both x's, I have summation n equal to 1 to infinity a sub n times x to the power n. And then my plus 2, and just repeating my power series, my first one, equal 1 minus x squared. Okay, so now this is what it looks like after we're done with our first step. That is substituting each of my y terms into my main differential equation. Now we're going to do our second step, which is to match our exponents to x to the power n. So basically, these ones needs to be an n. And I can already see that my third power series and my fourth power series already has a power of n. So that means I don't really have to do anything with them. I don't have to try to change them or anything. So the only one that needs to be transformed is my first power series and my second power series, since they have powers n minus 2 and n minus 1. Okay, so let's go ahead and do that. So now first I want to shift my change the exponents of my first power series, which is this one right here. So I'm going to do that. So I have summation n equal to 2 to infinity a sub n times n minus 1 x to the power n minus 2. And I want to transform them such that, let me use a blue color. Okay, the power of my x now becomes just an n. All right, so if you look carefully, all I need to do is add 2, and I can see that my negative 2 and my positive 2 gets canceled, so I'm just left with n. So all I gotta do is add 2 to all my n's. Okay, so if I do that, that means my a sub n now gets transformed to a sub n plus 2. Then again, my another n gets also transformed to n plus 2. And then I have my n plus 2 minus 1, which is basically n plus 1. All right, so since all my n's increased by 2, that means my starting index decreases by 2. So instead of starting from 2, it's going to start from 0. Okay, so this is what it looks like. All right, so now I can see that the power of my x is now n. Okay, so exactly the thing that we're looking for. All right, so now let's transform our second power series. So I have summation n equal to 1 to infinity a sub n times x to the power n minus 1. And then let me use a different color. Okay, I'm going to use this dark green. So now it also needs to be transformed to just an n. So all I got to do for this case, I need to add 1 to it. So the negative 1 and the positive 1 gets canceled, so I'm just left with an n. That means all my n's in my power series increases by 1. So from a sub 1, it now increases to a sub n plus 1. And then I have my n, that is now n plus 1. And since all my n's in my power series increased by 1, that means the starting index will now decrease by 1. So instead of starting from 1, it's going to start from 0 to infinity. Okay, so now let's rewrite our transformed power series into a differential equation. So I have my first transformed power series, which is summation n equal to 0 to infinity a sub n plus 2 times n plus 2 times n plus 1 times x to the power n. And then I have my second transformed power series, which is summation n equal to 0 to infinity a sub n plus 1 times n plus 1 times x to the power n. And then I have my minus, and then I have my third power series, which is the same, since they have the exponent n, the exponent of x is n. Okay, and then I have my plus, since I'm running like a little out of space, so I have summation n equal to 0 to infinity a sub n times x to the power n equals 1 minus x squared. Okay, so this is what it looks like after we have matched our exponents to n. Okay, so this is my new differential equation now. Now my third step was to shift our indices, so these ones right here, so that they all have the same starting index. And I can see that three of the power series have the starting index 0, and the other one is just 1. And like we mentioned earlier, we always try to shift the indices of the smaller power series. Now I can see that 3 of these power series have the starting index 0, and the other one has a starting index 1, right? So that means we shift the indices of the power series with the smaller starting index, that is 0, to match the one with the larger index, which is 1. Okay, so in this particular example, I can see that I need to shift the indices of my first one, of the first power series, my second power series, and my fourth power series, okay? I need to shift the indices of these 3 power series. Now, to be able to shift these 3 power series to start at an index of 1, we need to write the term for n equal to 0 separately. Okay, so we need to write the term n equal to 0 for my first power series, my second power series, and my fourth power series separately, so that we don't lose these terms. Okay, so when n is equal to 0, if we substitute into our first power series, gives 2a sub 2. Okay, so all I did was just substituting n equal to 0 directly into my expression. Okay, then I have my plus, and now I can shift my indice to 1. Okay, since I've already written my n equal to 0 separately. Okay, so using that same blue color, I have summation n equal to 1 to infinity a sub n plus 2 times n plus 2 times n plus 1 times x to the power n. And then I have my plus. Again, just plugging in my n equal to 0 directly into my second power series, and that gives a sub 1, okay, because 0 plus 1 is just 1, and then I have a sub 0 plus 1 again is 1, and then x to the power 0 is just 1. Okay, and now I can shift my indice to 1. So again, using my green color, I have summation n equal to 1 to infinity a sub n plus 1 times n plus 1 times x to the power n. And then minus, again, I don't have to write any terms separately for my third one because it's already starting from 1, okay? So summation n equal to 1 to infinity a sub n times x to the power n. And then I have my plus. So my fourth power series, I have to write my n equal to 0 term separately since it starts from 0, and I want to be able to start it from 1. So in that case, if I just plug in my 0 into my second power series, I have 2 times a sub 0 times x to the power 0, which is 2a sub 0. Just write 2a sub 0, and then my plus, and then just writing my index. Whoops. Okay. And now it's going to start from 1. Okay. Oh, cannot forget my 2. A sub n times x to the power n equals 1 minus x squared. Okay. So this is my differential equation after I have shifted our indices so that all of them start from 1, start from the bigger indice. Okay, so this is what it looks like after we have completed those 2 conditions. That is making sure that my exponents, they all have the power n, And also that their starting indexes, they have the same number. They have the same starting index, okay? So we have made our exponents or powers of x to n, and we have also shifted our indices to the power series start from 1. So now we're ready to combine the power series to just 1, okay, since their power series match. So does the starting index, okay? So now what I want to do, I just want to write the constants first, okay? So the smallest number I have is 2a sub 0. I'm going to write that first. And then I have my a sub 1 plus 2a sub 2. Again, these are all my constants, okay? And just writing them in order, it's not necessary. I wrote them in like my increasing order, since when I write my final solution, I can see that my a sub 0 always comes first, okay? And then combining all these 4 power series to 1. So I have summation n equal to 1 to infinity x power n. And then just writing out my leftover terms. So I have a sub n plus 2 times n plus 2 times n plus 1. And then I have my plus. And then now writing my second power series. So I have a sub n plus 1 times n plus 1 minus, and then I have my third power series, okay? So I have a sub n times n, and then my fourth power series, which is 2a sub n equals 1 minus x squared, okay? So I've also combined them into 1, all my 4 power series into 1. Now my fifth step would be solving for these coefficients, right? Getting the values for my a sub 0, a sub 1, a sub 2, and the rest of my a subs, okay? So let's go ahead and do that. So to be able to find my coefficients, the first thing we are going to do is we are going to write our constants, right? And I can see that these 3 terms are my constants because they don't have any x attached to it, okay? So let me write them together. Again, the only reason why I'm writing them together, it's because they are constants. They have no x attached to them, okay? If one of them had an x, then that part wouldn't be included here, okay? They wouldn't be written together, okay? And then we are going to look at our right and see if we have got any constant value to match what we have for our left-hand side. And I can see that at my right, I have 1. I have 1 as my constant value. So that means my left-hand side equals the value I have gotten for my right-hand side. So that means this entire thing is equals 1, okay? Now, we don't know either of these 3 values, right? We don't know the value of a sub 0, we don't know the value of a sub 1, and we don't know the value of a sub 2. And in our main differential equation, we are not given any initial value either, okay? So since we are not given any initial values, and that means I will have arbitrary numbers. And how many of these 3 would be my arbitrary number? Well, it depends on the order of my differential equation. And for problem number 9, my order of differential equation is 2 because I have my second derivation here. So that means I'll have 2 arbitrary numbers. And conventionally, I always take my a sub 0 and my a sub 1 as my arbitrary numbers, given that their values are not given, okay? So taking my a sub 0 and my a sub 1 as my arbitrary number. Okay, so in that case, my a sub 2 would be 1 minus 2a sub 0 minus a sub 1 divide by 2. So if I want to write them separately, I can also do that. So I have 1 by 2 minus a sub 0 minus 1 by 2 a sub 1. So this is my coefficient for a sub 2. Okay. So I have coefficient for my a sub 0, which is an arbitrary number. I have a coefficient for my a sub 1, which is also an arbitrary number. And now I have a coefficient for my a sub 2. Okay. Now in my question, I need to generate 5 terms. So I need to find my other coefficients for that. And for that, I'm going to use my beautiful power series over here. Okay. So let's go ahead and do that. Now, remember that this power series are only applicable when I have an x, okay? So these are my coefficients for different powers of x, okay? And at the other side, I just have constants, okay? So whenever I have my coefficients, okay, they will be in this power series form, okay? All right, so when n is equal to 1, okay, then just so plugging my n equal to 1 in this entire power series thing, I have x, which is the power of 1, and then I have a sub 1 plus 2 times 1 plus 2 times 1 plus 1 plus a sub 1 plus 1 times 1 plus 1 minus a sub 1 plus 2a sub 1, okay? Now, if I simplify that, I have 2 plus 1, that is 3, and then 1 plus 1, that is 2. So 3 times 2 is 6. And then I have a sub 3. And then plus 1 plus 1 is 2, and then a sub 2. And then I can simplify that. So I have a sub 1, negative a sub 1 plus 2a sub 1. That is just my a sub 1. Okay, and if I look at my right hand side and if I try to find the coefficient for my x, I can see that it's going to be a 0 because there is no coefficient, there's no x at my right? So I just have a constant. Let me use a different color. Let me use purple. Okay, pink. So I have a constant and I have a coefficient for x squared, not x. Okay, so that means there is no coefficients for x or greater than 2. Okay, so there's only coefficient for x squared and there's one constant. So that's just 0. So now just taking out my x's, I have 6 a sub 3 plus 2a sub 2 plus a sub 1, that is just 0. Now I know that my a sub 1 is an arbitrary number, and I know my a sub 2 is this value right here. So let's plug in the value. So I have 2 times 1/2 minus a sub 0 minus half a sub 1, and then my plus a sub 1 equals 0. Now if I simplify that, so I have 6a sub 3 plus 1 minus 2a sub 0 and then minus a sub 1 and then plus a sub 1 equals 0. Now I can see that my negative a sub 1 cancels out my positive a sub 1. So I have 6 a sub 3 equals 2 a sub 0 minus 1. Then taking out my 6 at my right hand side. So I have 1 by 3 a sub 0 minus 1 by 6. So that is my coefficient for a sub 3. Okay. So now let's go ahead and find the coefficient for another term. So when n is equal to 2, so if I look, if we go above, I have x squared because now n is equal to 2. And then I have my a sub 2 plus 2 times 2 plus 2 times 2 plus 1, and then plus a sub 2 plus 1 times 2 plus 1 minus a sub 2 times 2 plus 2a sub 2. So writing all of that terms, okay, I have x squared. So I have a sub 2 plus 2 times 2 plus 2 times 2 plus 1 plus a sub 2 plus 1 times 2 plus 1 minus 2a sub 2 plus 2a sub 2. Okay. And if I look at my right hand side, I have negative x squared. Okay. So I have negative x squared. Now simplifying them and taking out my x squares. So I have 2 plus 2, which is 4, and 2 plus 1, which is 3. So 4 times 3 is 12, a sub 4, plus 3a sub 3, and then my negative 2a sub 2 and my positive 2a sub 2 cancels out each other. And then I have negative 1. Okay, so now again, substituting my a sub 3 inside here. So I have 12 a sub 4 plus 3 times 1 by 3 a sub 0 minus 1 by 6, negative 1. Now if I do all the simplification, okay, I'll get, a sub 4 equals negative 1 by 24 minus 1 by 12 a sub 0, okay? And this is my a sub 4, okay? And then similarly, let's do for n is equal to 3. So when n is equal to 3, again, plugging in my n equal to 3 into my expression, I have x cubed a sub 3 plus 2 times 3 plus 2 times 3 plus 1 plus a sub 3 plus 1 times 3 plus 1 minus 3a sub 3 plus 2a sub 3. Okay, so all I did was just plugging in my n is equal to 3 over here. Okay, and then again at my right hand side, I can see that there's no coefficient for x cubed. So again, there's no coefficient for x, and there's no coefficient for x power greater than 2. Okay, so this is also going to be a 0. Okay, so I have 0 x cubed. Now taking out the cubes, x cubes, I have 3 plus 2, which is 5, and 3 plus 1, which is 4. So 5 times 4 is 20, a sub 5, then plus 3 plus 1, which is 4, then a sub 4, and then I have negative 3a sub 3 plus 2a sub 3, which is just negative a sub 3 equals 0. So I have the value for both a sub 3 and a sub 4. So if I just plug in those values, so I have 4, negative 1 by 24 minus 1 by 12, a sub 0. And then I have my a sub 3, which is negative 1 by 6 plus 1 by 3 a sub 0. Okay, just making sure all my coefficients stays in the same place. Okay, equals 0. Now again, if we simplify all of that, I get a sub 5, which is 1 by 30, a sub 0. Okay. All right, and then I have n equal to 4. So I have x4 times a sub 4 plus 2 times 4 plus 2 times 4 plus 1 plus a sub 4 plus 1 times 4 plus 1 minus 4a sub 4 plus 2a sub 4. Again is 0x4, because I can see that I don't have any coefficients for x which has a power greater than 2. Okay, so just taking out my x powers, taking them out, I have 4 plus 2, that which is 6, and then I have 4 plus 1, which is 5. So 6 times 5 is 30, and then I have my a sub 6 plus 4 plus 1, which is 5, and then I have my a sub 5. So I have 5 times a sub 5, then minus, and then I have 4 plus 2, that is negative 2a sub 4 equals 0. Now substituting my a sub 4 and my a sub 5 into this. So I have 30 a sub 6 plus 5, 1 by 30 a sub 0, and then minus my 2a sub 4, which is negative 1 by 24 minus 1 by 12 a sub 0. So I have 1 by 24 and then I have by 1 by 12 a sub 0. That is equals 0. So I have 30 a sub 6 plus 5 by 30 cancels out, so I have 1 by 6 a sub 0. And then I have plus 1 by 12, and then I have plus 1 by 6 a sub 0 equals 0. And again, if we simplify them further, I have a sub 6 equals negative 1 by 360 minus 1 by 90 a sub 0. Okay, so now I have my coefficients for my a sub 0, which is an arbitrary. I have my a sub 1, a sub 2, a sub 3, a sub 4, and a sub 5, and also a sub 6. So I think we are ready to write out our terms. Okay, so I have my general solution. So I have my a sub 0, and then plus my a sub 1, which is also an arbitrary number, x, and then I have my a sub 2. Again, my a sub 2 was, if you remember, it was half minus a sub 0 minus 1 by 2 a sub 1. So if I just go back just to check, I have half negative a sub 0 and minus a sub 1. And then I have my a sub 3, which was negative 1 by 6 by plus 1 by 3 a sub 0. So just substituting all the values I've gotten. And then I have negative 1 by 6 plus 1 by 3 a sub 0 x cubed. Then I have my a sub 4, which was negative 1 by 24 minus 1 by 12 a sub 0. So I have negative 1 by 24 minus 1 by 12 a sub 0 x to the power 4. Then I have my 1 by 30 a sub 0, and that is x to the power 5. And then I have my 1 by for my a sub 6, I have 1 by 360 minus 1 by 90 a sub 0 x to the power 6, and then so on. Now, this could be your final solution. Like I said earlier, right? If you don't want to do anything, just keep this as it is. You are more than welcome to do that. But like I have done in my previous other videos, that you can either choose to keep it as it is, or if you want to further simplify that, so you can also do that. So if you're like me and you want to further simplify, so the way we are going to do is, we can see that we have, since we have our two arbitrary numbers, I have a sub 0s and a sub 1, and then I also have constants, so I can keep all these three terms separately, okay, like together, so grouping them into a sub 0s, a sub 1s, and all my constants. So let me mark all my a sub 0s. So I have a sub 0 over here, I have an a sub 0 over here, then a sub 0 over here, a sub 0s over here, and then a sub 0s over here. Okay, so I'm going to write my a sub 0. Then I have my 1 minus x squared plus 1 by 3x cubed. And then I have my minus 1 by 12 x to the power 4. Oh, I also have an a sub 0 over here as well. Okay. And then I have my plus 1 by 30 x to the power 5. And then I have 1 by 90 x to the power 6. And then so on. And then I have my a sub 1, which is in green. So I have a sub 1 over here and a sub 1 over here. And I can see that's about it. So you can write that. So I have x and then minus half x squared. And then writing all the constant terms. So I have this one. And then I have a constant over here, I have a constant over here, I have a constant over here. So you can go ahead and do that. So I have half x squared minus 1 by 6 x cubed minus 1 by 24 x to the power 4. And then I have negative 1 by 360 x to the power 6, and then so on. Okay, so this is the second type of solution where you want to simplify them further, where you want to group them separately. Again, this is not mandatory, it's completely optional. If you don't want to group them, that is absolutely fine. And if you want to group them, then your solution would look like this, would look something like this. Okay. All right, so I hope you guys enjoyed watching this video as much as I enjoyed making them, and I will see you in my next video. Bye!